All right. So today we're going to finish up the packet. The first thing, and I kind of skipped a few slides, so go ahead and find this one. Real quick, single replacement reactions. You know, in the past we had to look at the activity series to determine if a chemical reaction or a single replacement reaction could occur. But in the AP world, what you do is just assume that it always works. There will never be no such thing as no reaction in a single replacement perspective. Okay. So what I want to be able to do is I want to be able to do net ionic without having to worry about the reaction as far as words. So let's just jump right in. The first rule of your balance, bust, and cancel is, as far as balancing and busting, what things do you never bust? Solids, liquids, and gases. If it's a solid, a liquid, or a gas, what do? Leave it alone. What's the only thing you can bust? Aqueous. Very good. So the first one says solid magnesium is added to copper 2 nitrate. So as soon as you see that word solid, what does that tell you about the magnesium? Leave it alone. So Mg+. Now, this is when you have to know your solubility rules. Okay, this is what you were working on yesterday. Does it say what state copper 2 nitrate is in? No. We're going to assume that it's going to be an aqueous solution. Okay. Normally they tell you if it's a solid, or liquid, or gas. If it doesn't, they would have to just kind of assume it's aqueous. Based on solubility, is there anything we can get rid of? What? I can get rid of nitrate. I know that it's never gonna be there. Okay. So does that leave me something left? What? I'm going to do something really dumb. Is that what it means by copper 2? Is that what it means by copper 2? Is that what it means by copper 2? So this is what it's referring to. Remember, the Roman numeral is reference to what? The charge. Fantastic. So now we know that these two things are going to react. If we were to write out or say the whole reaction, this is a single replacement. Magnesium is going to swap places with who? With copper. Why is it going to swap with copper? Metals replace metals. So copper is going to end up with who on the other side? Copper is going to end up with who? Nobody by itself. So we know that it is going to go from copper ion to copper what? Solid. Magnesium is going to end up with who? Nitrate. So it's going to go from the solid form to what? The aqueous or its ion form. Yeah. Simple question. Is it balanced? Atoms? Yes. Charge? Yes. If I ask the following question, part B, which species is oxidized? Who would it be? Magnesium. Magnesium is oxidized. How do you know? 0 to 2 plus. I think you're starting to get the hang of it, right? Okay. Do you really even need a half reaction for this? No. It's done. There's nothing you really need, right? Okay. Jamila, go ahead. Very good. Because if you were to write out the whole thing, it would be there and you would see it. But because nitrate's soluble, you bust it and get rid of what stays the same. Very good. Yes. This is net ionic. Without the busting. What we're doing is where I wanted us to get. Without having to write the whole thing. Without having to bust it. Without having to cancel it. We are jumping off into the deep end and going right in and out of it. It's the same thing. Yeah, okay, so double, this is single. Yep, go ahead. Because there's no hydrogens and no oxygens present. Okay? Real quick, and this is important. If we did set up a half reaction, now I'm going to ask this, and some of you may remember. If you don't, that's fine, but I need to ask it. What would the value of N be? N of what? Electrons. What would be your value of N? Y2. Very good. So if I need to go from magnesium to magnesium ion, how many electrons were lost? 2. To go from copper ion to copper, how many electrons were gained? Does that make sense? So you can visually also figure out your N, which is your number of moles of electrons. And again, I've already showed you this. When we get to electro, we're going to have this formula where this is going to be very important. You have to know how to get in to be able to calculate this. Okay? Yes, sir. Two moles of electrons. It's moles of electrons. It's not just 2 electrons. Because do you agree that whenever we do our mole-to-mole ratio, it's a coefficient? So for every 1 mole of magnesium, to get to 1 mole of magnesium to ion, I need 2 moles of electrons. Things don't just transfer in individuals. They transfer in values of moles. Does that make sense? Mason, no? Okay. Do you agree that your coefficients represent your mole-to-mole ratio? Okay, so for every 1 mole of magnesium, I've got 1 mole of magnesium ion. How did I go from magnesium to magnesium ion? Do you agree that 2 electrons were lost? But was it physically 2 electrons? It was 2 moles worth of electrons. Because it was one thing than just 2 physical electrons. There's 2 moles worth, which is 1.204 times 10 to the 24th. That's Avogadro times 2. 6.02 times 10 to the 23rd times 2. Do what? Okay. All right, let's look at the next one. Chlorine gas. As soon as you see that word, what does that tell you? Very good. Cl2. Fantastic. Okay. Chlorine gas is bubbled through a solution. Let me ask you this, and I want you to just kind of think with me. Think analytically. Had it just said chlorine gas is bubbled through through sodium iodide, if this word had been left off, how would you still know sodium iodide was a solution? Bubbles. Did you say bubbles? I apologize. I heard a bunch of other bad answers. Okay. Bubbled. That's very like non-assuming that cool. It's a bubble. But what does a bubble mean? What is it? It's a gas in a liquid. You're learning, right? How clutch is that? Okay. How clutch is that? A gas in a liquid is a bubble. Now, obviously, sodium iodide is not a liquid because it's an ionic compound. So it has to be in the solution form. Now, we are going to learn about something later called a molten solution, and that's where it gets kind of weird. And just kind of follow along with me. Is it possible to melt salt? Molten solution is melted solid. Like literally melted into the liquid. You didn't dissolve it. You didn't boil it. You took that solid and got it so hot, it liquefied. Sure, okay. But it's a liquidy solid. That's how hot it got. And we'll talk about that later, okay? You're thinking too much. Quit. Okay? So, we know that this is a solution. So is there anything we can cross off and get rid of? What? Okay, sodium. Okay. Now, we know that this is a iodine is left, so it's going to be I minus. Now, this one's a little bit different because earlier we said we know that magnesium swap places with copper because metals replace what? Metals. But let's look and see what's by itself. We got chlorine. Chlorine is a what? A gas or what type? It's a non-metal. And what do non-metals replace? Non-metals, very good. So we know Cl is going to swap with iodine and going to end up with sodium. But we know sodium's a spectator, so we don't need it. So Cl2 turns into what? Cl minus. And I goes from the ion state to what? Okay, so here's the deal. Do you agree that chlorine, Cl2, reacted with sodium iodide? Cl and I swap places. So Na and Cl are now together. Is that a brand new compound? Check your charges. Na plus, Cl minus. Where did the Na go? It's spectator, get rid of it. We don't need it. So that's why I went from Cl2 to Cl minus. The only time you put a 2 is when it's by itself in its elemental state. Okay? Hold that thought. I've got a very important question. If I asked you to assign states of matter to this, matter of fact, I'm not going to ask you. Do it. Put the S, the L, the G, the AQ behind each one of those. See if you can do that. Keep your head down. Don't look up there. Nothing. Don't ask a question yet. All right. Everybody done? So here's my first question. What state of matter would you have put for chlorine? Very good. It's a gas. What about I minus? Aqueous. What about chlorine ion? And what about iodine? It is a solid. Exactly. This is one of the odd things about the halogen group. Look up there on that periodic table. And matter of fact, it's not. Let's look at the back one where the lights are on. It's a little easier to tell on that one. Look at your first two halogens. What color are they? They're red, which means they're in what state? Gas. Then look at Br. It's blue. There are two blues up there. Bromine and who? Mercury. And then look at I. It's black. It's a solid. So that's one of those weird, strange, odd things that a lot of people forget about, but is very true and important when we're talking about the halogens and single replacement reactions, because iodine actually turns into a solid. Okay, it sounds weird, but it is a fact. Yes, ma'am. Yes. No, you don't have to. The whole reason I asked you guys to do that was for the solid. I wanted to see if you remembered iodine was a solid. We're not finished, sir. That's one of those weird things you got to memorize. Yep. Other than those red things up there or the two blue things. And again, I know that's kind of aggravating, but it's that is one of the things about AP that they expect knowledge and use, so you memorize those few things. So only the things in red are, now you got to remember, and I should have said this before, the color comes from what it looks like at room temperature. All of those things can become a solid. All of those things can become a gas. It's at room temperature. And that's one of the things that I probably never ever said to you guys, what you're sitting in. It's assumed 25 degrees Celsius, which is about 77 Fahrenheit. Now I know that's not room temperature, but they assume it at 25 degrees Celsius. Yes. Don't I have no idea. I have no idea. So the thing that Esteban brought up, yes. What? How do I turn a gas into a solid? I can drop the temperature, or as Justin wants to bring up, you can increase the pressure. Okay. Can you see frozen carbon dioxide? Yeah, go to Publix and buy dry ice. Okay. All right. So you can freeze oxygen, just like nitrogen. Nitrogen is at room temperature a gas. There is such thing called liquid nitrogen, and it's really freaking cold. Okay, to get it to become a liquid, it's like negative 200 something Celsius. Yes. There's a lot of stuff you can't eat. Yeah, I mean, almost everything. You can't eat either one of them. If you pour liquid nitrogen on your throat, it would kill you. No. You're not putting it in the ice cream. You put it on the bowl. Yeah. Yes, sir. That's a really bad idea. That's a bad idea. That's cool. I've never heard of that. Okay, last thing. Finally, Esteban, you brought up the fact that it's not balanced, and you're right. It is not balanced. So I would need to come in and put a 2 here and put a 2 here to balance it. And again, I'm going to ask the same question I asked earlier. What is your value of n? 2. 2. Okay? All right. Real quick, you do the last one. I'm not going to spend any time discussing it. You guys do the last one real quick. See if you can come up with the answer. You're going to have 15 minutes to do this. I'm going to write it up here. So solid zinc, which is Zn plus solution of lead 2 nitrate. I've got Pb2 plus. Metals replace what? Metals. So you should have Zn2 plus Pb solid. What's your N? 2. Do you need to balance it? It's already balanced. Very good. All right, finally, 3 questions 30 minutes later. So let's do solution stoichiometry. Okay, this is a review of everything. When an aqueous solution of sodium hydroxide and iron 2 nitrate are mixed, a red gelatinous precipitate forms. Very good. How do you know it's a chemical reaction? A color change and a precipitate forms. Very good. Okay. Calculate the mass of the precipitate form when 50 mils of a 0.2 sodium hydroxide is combined with 20 mils of a 0.125 molar iron 3 nitrate solution. Before you do anything, the first thing I want you to do is write the net ionic equation for that reaction. See if you can get the net ionic equation. I'm going to ask this question. It's rhetorical, which means do not answer it. Anywhere in the data, and again, do not answer this, do they tell you what the solid is? Think about that as you go. All right, so let's look at the net ionic again real quick. I just want to make sure everyone heard me when I said it. In the equation, I know there at the very bottom it says iron 3 nitrate. Change it to 2 because the problem up there at the top says 2, so let's make it 2. All right, so again, once you visualize how to do all this, it's going to make net ionics easier. So we're going to cross off everything that will never make a precipitate. Is there anything in the first formula? Sodium, how do you know? It's a group 1. Get rid of it. We don't need it. What about iron 2 nitrate? Get rid of it. So then the question becomes, the only thing you have left is hydroxide and iron 2. Is that, based on solubility rules, a possible precipitate? Yes, very good. All right, so we know that it is going to be OH minus plus Fe2 plus yields FeOH2. Getting better at this? Now let's look at the data. Very good. Thank you. My apologies. I always forget that. I need 2 hydroxides. What would be your N value? 2. And again, guys, I apologize. Not every time will N be 2. Okay? Don't think that. We will, not on this one, but we will get to, like, I'm asking it now, so when you do get to that, you're like, got it. Okay? All right. So, what is the question? Okay? We need to know the mass of the precipitate. So, we're trying to get to that. That's my question. Now, we've got to look at the data we have been given. So, we've been given 50.00 mils of a 0.200 molar solution of the hydroxide and then 20.00 mils of a 0.125 molar solution of that. The first time students see this, they freak out. The reason they freak out is because the words in the problem do not match the formula. What I mean by that is because it says when 50 mils of a 0.2 molar NaOH. When you look at the reaction, that just says OH minus. Very good. You're exactly right. Has nothing to do with it. Because it's sodium still floating around. You just don't have to tell me that it's there because I don't need to know about it. We still have to use the data as it is given. Now, my question to you is, which one of these two beautiful pieces of data do I take to get to the other side? I don't know yet. Got to find the limiting reaction. Now, let me ask you something. When we're trying to solve for the limiting reaction, would you rather be given volume and concentration or grams? This is so much easier because do you have to find the mass of either one of those? How do you get from volume and concentration to moles? Multiply. Now, the problem is, can we take the data as is and get there? No. We got to change one thing. What's the one thing you got to change? All right, milliliters or liters. Now, you guys know you can move it mentally. Would you say it's 0.05? No, because molarity is mole per liter. Technically, that would change. It would tell you who the limiting reactant is. Doesn't matter. That'll give you the limiting reactant. However, your number of moles will be off by tens place. Or actually 3/10 places. Because you got to change it. Exactly. All right, so help me out here. What is the number of moles after moving the volume of hydroxide? Like that? Okay. Moles. All right. And then what is the moles of the iron 2 ion after moving the decimal? Now, we can't forget of what our limiting reactant formula is. It's the moles divided by the coefficient. Again, this step is an identifier only. All it is used for is to say, ding, 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 ding. Here I am. Hi, I'm the limiting reactant. What's wrong? Oh, my bad. Yep, that's wrong. Thank you. What's wrong, Trevor? Is the math wrong in the second? Where? That's... Do it again. Okay. Now, then divide 0.0105 by 2. And is it less than the other one? What is it? 0.00525. So which one is less? Iron. So this is our LR. Okay. Now what do? We use the moles of iron to go to... No. To the grams of FeOH2. All right. So we've got 0.00250 moles. I know, I agree with you. That's why I leave them off half the time. Okay, so we've got moles of Fe2 plus to moles of FeOH2. Dustin, do you have the mass ready? Thank you. $89 point what? Okay? Now, what? Nope, not a bit. Because you remember, we're really working with iron 2 nitrate. You just happen to see the iron ion as the only thing written. Don't overcomplicate it. Alright. No. That came from that thing because it's a solid. Remember? Yes. I went from moles of the iron ion to moles of the solid precipitate. Yes. Bingo. Yeah, because you couldn't do grams the way we have it written because you're missing part of it. Okay. All right. What is your mole to mole ratio of these two things? 1 to 1. 1 to 1. Chance, you got an answer? Pause before you say it. How many significant figures must your answer be? 3. Because if you look at your volumes, they're both 4, but we only need 3. Go ahead. That's a really bad 5. Yes, the least number of significant figures. So 0.225 grams of iron 2 hydroxide. Solid. It's the least number of decimal places. Yes, sir. Any questions on that one? Very good. Let's move on to the next one. What volume, this is a lot easier. That was a long one. What volume of a 0.25 molar sulfuric acid is needed to react completely with 35 milliliters of a 0.35 molar barium hydroxide? So they ask you about a volume. They give you 2 concentrations in another volume. Do we have a formula for that? All right, so M1V1 equals M2V2. We've got MSVS equals MDVD, and we've got MAVA equals MBVB. Which one am I using? Why am I using the AB one? Very good. It is an acid. Okay? It is an acid, and that is a base. It doesn't. You don't know. You definitely. I mean, same formula, but the letters are important here. You're going to get the right answer, but we're not stock and dilute. We're neutralizing. Okay. And let me tell you this also. Remember, if it's S and D, stock and dilute, it's the same compound. Because if I have sweet tea, am I diluting it? Is it still sweet tea? Here, I'm using sulfuric acid and barium hydroxide. Those are different. The answer will be the same, but it's the letters that are important. Now, so my question to you is, which variable am I solving for? Very good. VA. All right, so the molarity of the base is 0.350. The volume, can I leave it in milliliters? I can in this case. So 35.00 mils. And again, if it makes you feel better to convert it to liters, by all means, do whatever makes you feel better. Doesn't matter to me one bit. Anybody got an answer? How many significant figures? Thank you. Yeah, sorry. I was just fixing to get out of my mouth. Write the formula for sulfuric acid. It is a strong acid. It is a strong. All right, so if we were going to titrate these, what would be the equivalence point? 7. Which one wins? Neither. Strong, right? How much time we got left? Sheesh. I got one. It's dead. All right. Let's look at this reaction. All right. I can't not wear it. I feel naked if I don't wear it. It doesn't work. It's been dead for months. It is bad. Looking at this reaction, has the half reaction process already been done for you? Yes, it has. Okay, the way you can tell is it's already got the hydrogens, it's already got the waters, and everything's already balanced out. This is a really good question. If I can figure it out. Hold on a minute. Here's my question. No, hang on. I can't figure it out from here. It is. Here was what I was fixing to ask. But you can't figure it out from here. My question was, what is your N value? You'd have to do it backwards, and I'm not worried about that. It's either 10 or 5. Because you see going from Fe2 plus to Fe3 plus is 1 electron. No, it has to be 5. Stay with me. Do you agree that going from Fe2 plus to Fe3 plus, first of all, do I need any waters or any hydrogens? No, are the atoms balanced? The charge is not, right? So that means I need 1 electron on that side. Does that make sense? Okay, so here's my question. We go back and look at this. What did your irons have in front of them now? What's the only way that it could have gotten a 5 in front of it? Because you multiplied that by 5. So your N value would have been 5 in that case. Does that make sense? Okay, and it doesn't. Like, so you had to multiply this entire thing by 5 to get that to cancel with the other half. No, I said I wanted to know what your N value would be, your moles of electrons for this. So like, what was the number of electrons you canceled off and left out? It would have been 5 in this case. Okay. Does that make sense though? But again, I'm only looking at this half. That's it. So to go from here to here requires 1 electron. Okay. Well, if I didn't need to multiply this by anything, it would be 1 Fe2 plus and 1 Fe3 plus. But the reaction has it as 5 Fe2 pluses and 5 Fe3 pluses. How do we get a 5 in front of these two things? You had to multiply both of them by 5. Well, since it was 1 electron, what's 1 times 5? 5. That has to be your N. Trevor, does that make sense? I'm not. You do. It's the first thing I need to add. Now I need electrons, right? I've got a positive 7. I've got a positive 2. What do I need? 5 electrons, which is why the top half had to be multiplied by 5 to get that to cancel. So what was the value that was canceled? Your N. 5. Now does that make sense? Yes, there should. It's distributive. No, what, like this goes to here, this goes to here, and that goes to there. It's distributive. All right, so let's just move on. So what volume of a 0.648 molar KMnO4? And I know what you're thinking when you read it. You're like, where the hell did that K come from? Right? It's a spectator ion. So technically, it's still floating around in there somewhere. We just don't need it. So what can you attribute that particular concentration to? Very good. So really, this is where it's referring to 0.684 molar. Is required to react completely with, and then it gives you FeNO3, 2. Where in the world did that nitrate go? It's soluble. I don't need it. So which iron is this one? It's the reactant one. There's two ways you know. Number one, it's iron 2, and the other one says required to what? React. That's where that comes from. And then it tells you that, so these two things technically belong with that one. So this is just like the last one, but is it acid-base? Is it stock dilute? Remember, stock dilute is the same compound. These are two different. So which one would this be? M1V1 equals M2V2. Okay. Does it matter which one is 1 and which one is 2? Doesn't matter at all. So we're just going to say that we are solving for V2. Actually, let's solve for, let's do, because it's listed first. That's exactly what I was fixing to say. We're solving for V1 because it's listed first. So that means that V2, well, thank you. So M2 V2 divided by M1. Alright, so the molarity of 1, the molarity of 2 is 0.250. The volume is 27.50 milliliters. And then the molarity of the top one is 0.684. Hey. Alright, so what's your answer? A number. Very good answer. Alright, so what is it? 10.1 ml MnO4 minus. Nope, you don't need to put K, sir. If you want to put it, sure, but do you need to? No. No. That's fine. Roll on with your bad self. Sir. Is what? E is, yes, is the moles of electrons. All right, so I'm going to give you guys an opportunity. We got a few minutes left for you to do it. I know that you're running out of room. This problem requires a half reaction. Okay? A half reaction. Hey, some of you takes a half sheet. So I at least want you to get through the half reaction first. Then see if you can do part B. I think B is easy. It's really easy, in fact. It's just like the last two things we've done. But see if you can do the half reaction and then see if you can do B. So here's the answer. This is a tough one based on the mere fact that the one thing that most students forget is this part right here. They forget to come in and double this. So remember, if you go back and look at the rules, one of the first rules is that you balance everything but the hydrogens and oxygens first. So save the H's and O's for last, and again you had to double it from there. So doubling that then affects your number of oxygens in the top one, but the reason you don't need 4 oxygens because of this and because of that is because there's already an oxygen present. So that's why that knocks it down. So hopefully you were able to get this this right. And again, don't forget at the very end, I know you know you've got water here, you've got water here, and then you've also got H's here and H's here. You have to combine like terms and cancel out what you have the most of.